I welcome all of you again to the second video lecture of this series. In the first lecture, we talked about analog and digital computers. This is just to understand what computers are and how they work. Our course will be on Fortran programming. So, the first actual topic as regards to programming is concerned is algorithms and flowcharts. So, what are algorithms? What is an algorithm? An algorithm is the step-by-step instructions to solve a problem. Knowingly or unknowingly, in our daily lives, we keep on using algorithms. Whenever we are faced with any problem, we need a solution, we chalk out the steps that we will take to solve the problem. That itself is an algorithm. In programming, what we do is we write down the steps one by one. That is an algorithm. Say, for example, the best example of an algorithm is a recipe. If you want to prepare a dish, you need to write down the recipe step by step. So that is an algorithm. So there are certain characteristics of an algorithm we'll discuss. So here you can see the picture. It states 2 is equal to a number, 1 is equal to a number. So the inference is 2 is equal to 1. If I go for this inference, my inference will not be logical. It's illogical. So the first requirement of an algorithm is the steps should be logical. One should follow logically the other. So taking the example of preparing a recipe, if I write, say, step 1 should be start or light the burner, then step 2 should be put the pan on the gas stove, step 3 should be put the ingredients or put oil. If I write it the other way around, put the ingredients first and at last, put the pan on the gas stove, that won't be logical. That is what I mean by logical and illogical. So in an algorithm, the steps should be logical. Second, if you can see the picture here, if I ask you what do you see, depending on your perception, somebody will say I see a beautiful young girl with the eyelashes here, then her nose here. Somebody else may say this is an old lady with an big nose. So this picture, what I mean to say, is ambiguous. It doesn't state clearly what it represents. So in an algorithm, the steps should not be ambiguous. It should be well defined and not ambiguous. Say, taking the example of the recipe again, if you just write put salt or put oil, if I don't say how much oil, the step becomes ambiguous. So you may not land up with your desired result. So this is ambiguity. So in an algorithm, the steps should be well defined and not ambiguous. Third, the number of steps should be finite. It can't have infinite number of steps because within a finite number of steps, we need a solution or a result. Consider a simple example of an algorithm. So the problem is to add two numbers. So what will be the steps for adding two numbers? The first step, of course, is to start. Then we input or read the two numbers. Then the actual process of adding the two numbers and store the sum. Call means we can call the sum, or we can call the sum as something and store it. We can call the sum as S or anything so that it becomes easier to output it. In a program, usually we do that. So the fourth step is to output the sum. If you're doing a problem, and you are not giving out the output, there is no meaning. So we'll add the two numbers, get the sum, store it, and output the sum. So the last step, of course, will be to stop. The next problem is to find out the sum of an arithmetic series. So it's characterized by the first term, the common difference, and the number of terms. So what are the steps to find out the sum of an arithmetic series? We won't be using the formula that we know from mathematics. Sum of an arithmetic series. We'll do it using a program, having some logical steps. What are the steps? To start, as the first step, input the number of terms, first term A and the common difference D. Third step, let us initialize, we call it initialization in programming language. Let the sum to be equal to 0 first, and we initiate a counter I is equal to 0. We call it a counter. It keeps track of the number of steps, or it will keep track of the number of terms that we have added in the series. So this is the actual operational part. Do sum is equal to sum, whatever value of sum was there before, plus a plus of id. Okay. So then do I is equal to I plus of 1. Then 7th step, check the value of I. If I is less than n, go back to 5. Write the value of the sum as and stop. So if you see the logic behind this, step by step we can see this, what happens. So let's say I'll just show you what will be the steps that will be followed. So first, what we are doing is we are initializing s to be equal to 0, right? So let's say what steps will be followed. First, we are initializing s to be equal to 0 and the counter I to be equal to 0, right? Then we are asking it to do s is equal to s plus of a plus I into d. So first step, what it will do, it will be s is 0 plus a plus of id. So if I have a simple series, let me say 1 plus 2 plus 3 plus 4, we have to sum this series. 1 plus 2 plus 3 plus 4. Here a is equal to 1 and d is equal to 1 and the number of terms n is equal to 4. So this is the first step. So it will be equal to 0 plus of 1. I is 0 here, so it will be 0 plus of 1. Then what we are asking it to do, counter increase I is equal to I plus of 1. Whatever was the earlier value of I, that was 0, so 0 plus of 1, I becomes equal to 1. Right? Then check the value of I. So I is less than 4. If I is less than 4, go to this step again. So what it will do, I obviously is less than 4, so I is equal to 1. So again it will do s is equal to s plus of a plus id. So what is the earlier value of s? This is 0 plus 1 plus a plus id means 1 plus of 1d. Okay, so this becomes equal to 0 plus 1 plus of 2. Then again we do I is equal to I plus of 1. So I becomes equal to, earlier it was 1, so 1 plus 1 becomes equal to 2. So 2 is still less than 4. Okay, so it is less than 4. So again it does s is equal to whatever earlier value we had, s plus 0 plus 1 plus 2, s plus a plus of id. So a is 1. So this is 1 plus of I is 2 now, 2 into 1. Right. So this becomes 0 plus 1 plus 2 plus 3. So we are getting the subsequent terms of the series. Then I becomes equal to I plus of 1. I was 2 here, so this becomes equal to 3. Still it is less than 4. So it will do one more step. S is equal to this value of S, 1 plus 2 plus 3 plus a plus of id, 1 plus of 3. That becomes equal to 0 plus 1 plus 2 plus 3 plus 4. We get the whole series. Then I becomes equal to I plus of 1, that is equal to 4. It is not less than n. N is 4. So what it does, it doesn't go back to step 5. So it proceeds. Right? So what it will do, it will then, now I is not less than n, so it doesn't go to 5, so it will go to the next step. What it will do, it will write down the value of the sum s and print it out and stop. Okay, this is how we write an algorithm for the summation of a arithmetic series. So let's go ahead. So next we have to talk about what is a flow chart. So a flow chart is nothing but a diagrammatic representation or a graphical representation of an algorithm. The same things, the algorithm we wrote down using certain symbols. We write down the flow chart. Some accepted symbols are there. Using those symbols, we can draw the flow chart. It's a diagrammatic representation or graphical representation of an algorithm. As I told, some specific symbols are used to represent different functions in the flowchart. So what are the symbols used in a flowchart? We use an oval which represents a start or end of the program or the algorithm. A rectangle, it represents a process like the summation process, doing the sum, finding out the product. This can be a process. A diamond indicates a decision, as we were talking about in the earlier algorithm. You have to check the value of I greater than n, less than n. That is a decision that the program has to make. So a diamond indicates a decision. A parallelogram represents an input or output. Because writing out the sum or inputting the first term, second term, first term, the common difference, that is the input. And output means writing out the sum of the series, sum of two numbers, product of two numbers. Circle, it represents a connector. If we have a very long flowchart, then a circle can represent a connector between the two parts of the flowchart. Then an arrow, it represents the flow lines, that is the flow of control in an algorithm or a program. For that matter, if we don't instruct the program to go back to a particular step, it will continue successively. It goes to the next step logically. For example, in the earlier algorithm for the sum of the series, if it is less than n, go back to step 5. So that going back or anything else, these flow lines, they represent the flow of control in an algorithm. Let's see some examples. The simplest example of a flowchart. Say, problem is to screen the items of your household. One fine morning you decide that there are too many things piling up in your household. You want to scan them and discard the unnecessary ones. So what will be the flowchart of your steps that will be taken? So I'll start, of course, oval represents start, then the process doing something, pick up the item, it's a rectangle, then the decision box. Does this item spark joy for me? Is it necessary for me? Is it not necessary for me? So this is the decision box. If yes, keep it and the thing that we are doing, or else throw it away. Then this arrow you can see, these are flow lines. Then the last step would have been stop. Because of lack of space I'm not showing it here, but it will be another oval here with a stop. This is simplest example of a flowchart, practical example. So let's see under flowchart, the one for problem for which we wrote down the algorithm. Flowchart looks something like this. It's an oval, start, input, parallelogram, x and y, the two numbers we want to add. The process sum is equal to x plus y, actual doing of the sum. Then the output, a parallelogram displays the sum, and stop or end. Flowchart to add two numbers. Simple one. Then we go ahead to the next one. Flowchart to find the largest of three numbers. It's an algorithm we did again. Start, oval, flow line. Logically it flows to the next step. Read the numbers A, B, C. Is A greater than B? Decision box. If yes, then again you have to check whether A is greater than C. If yes, then A is the largest number. If A is not greater than B, that means B is greater than A. Then we check whether B is greater than C also. If it is yes, then B is the largest number. Otherwise, if A is not greater than C, B also is not greater than C, no, then obviously C is the largest number. So this is the output parallelogram we are talking about. Then all of them, whether it comes this way, whether it comes this way, we have to stop. So this is a simple flowchart of the algorithm to find out the largest of three numbers. We are using the simple symbols at this level. For your level, these are enough, but these are not all. There are many other symbols used in complex flowcharts. We are not talking of them now. Let's see the flowchart to find out the roots of a quadratic equation. Of course, you have to start. It's an oval. Parallelogram stands for input and output. Input what? The coefficients A, B, and C. You can write input the coefficients if you want to be more clear. Then this is the process that takes place, rectangle. We find out the discriminant. Then the decision box. Check. If x is greater than equal to 0, either it's true or false, so you can write yes or no also here. If it is true, then the roots of the equation will be real. So find out the roots, x1 and x2, and print real roots, x1, x2. If x is not greater than equal to 0, false or no, then you can write the roots are not real. It's a decision, so you're telling it to stop. You can have another output box here where you can write the roots are not real and stop. Okay, so you can keep on making this complex so you can optimize it. In the algorithm we are talking about checking the value of A. So right here after this step you can put a decision box. You can do those yourself, try those yourself. Put a decision box here itself. Check the value of A. If A is less than 0, or if A is equal to 0 rather, you can directly say that the equation, you can have a branch here. If A is equal to 0, true, then an output box parallelogram, write the equation is not quadratic, and directly go to stop here. So you can have another branch here. I'm not showing it here, trying to keep it simple, but this itself can be more complex. Or here also you can have roots are not real, of course, you have decided. So you can of course find out the real part and the imaginary part of that complex root. That also can be done. So these are some things I'm keeping it for you. You can try and get back to me. So to find out, to draw a flowchart to find the sum of an arithmetic series. So the problem is to find out the sum of an arithmetic series to draw the flowchart. So I'll just try to show you actually how it can be done. So how we can draw it, of course, as we talked about, the first thing that has to be there is the oval where we write start. We need to start the process, then the flow line, then a parallelogram where we will read the values of read or input n, a, and d. Means read the number of terms of the series, the first term, and the common difference. Then we initialize the values of the sum and the counter we talked about in the algorithm. So sum we initialize it to 0, then the counter we initialize it to 0. Okay. After that, we ask the program to do this process. This is exactly from the algorithm that we had done. So we ask it to do s is equal to s plus of, s is equal to s plus of a plus of I into d. Okay, sorry for that, I'll write it here. S is equal to s plus of a plus of I into d. Right? Then, after it does that, ask the compiler to do another, increment the value of I. I will be equal to I plus of 1. Then the decision box. Check the value of n. Check whether I is less than n. If it is yes, this side. If it is yes, go back here. If this is yes, go back to this step and continue the process. If I is not less than n, then the output write the sum. Okay, then of course the oval to stop. So this is a simple example of a flowchart to find the sum of an arithmetic series. This slide I have kept it blank because I wanted to show you exactly how it can be done. So using these simple symbols, you can draw the flowchart. So what we have learned during this video lecture, I gave you an introduction to what is an algorithm and how you can draw a simple flowchart for the algorithm. Hope you will go through it, understand it, and take your own notes. Thanks for watching.